Picture a room with just 23 people in it. A small gathering. Now I'll make a claim that sounds absurd. There is a better than 50-50 chance that 2 of those people share the exact same birthday, same day, same month. Out of 365 possible days, and only 23 people, the odds are actually in favor of a match. Your gut is screaming that this is wrong, and I understand why. There are 365 days in a year. With only 23 people, it feels like there's tons of empty space on the calendar. Most people reason like this. For someone to share my birthday, I'd probably need a couple hundred people in the room. So 23 giving us even odds sounds impossible. But the impossible part is hiding in plain sight. Here's the mistake. You're thinking about you versus everyone else. But the question isn't whether someone shares your birthday. It's whether any 2 people in the room share a birthday. And that changes everything. Because we shouldn't count people. We should count pairs. Every possible pairing of 2 people is a separate chance for a match. So how many pairs are there among 23 people? Take the first person. They can pair with 22 others. The next, 21 new ones. And so on. The formula is n times n minus 1. All over 2. For 23 people, that's 23 times 22, divided by 2. 253. 253 distinct pairs. 253 separate chances for 2 birthdays to collide. Suddenly it doesn't feel so empty. We started by picturing 23 lonely people on a giant calendar, but hidden between them are 253 invisible connections, and each one is quietly rolling the dice against 365 days. Now let's actually compute the odds. There's a beautiful trick here. Instead of calculating the probability that some pair matches, which is messy, we calculate the opposite, the probability that nobody matches, that everyone has a totally different birthday. Then we just subtract that from 1. Line everyone up. The first person can have any birthday at all, so that's 365 out of 365. The second person, to avoid a match, must dodge that 1 day. 364 out of 365. The third must dodge 2 days. 363 over 365. Each new person has fewer safe days left. We multiply all these shrinking fractions together. Multiply 22 of these fractions. 1 for each person after the first. Each is just barely less than 1. So the product drifts downward. Slowly at first, then faster. By the time we've multiplied all 22, the probability that everyone is different has dropped to about 0.49. Roughly a 49% chance of no match at all. And now the reveal. If there's a 49% chance that nobody shares a birthday, then there's a 51% chance that somebody does. 1 minus 0.493 equals 0.507. 50.7%. With just 23 people, the coincidence is more likely than not. But why stop at 23? Let's watch what happens as the room fills up. Here's the probability of a shared birthday, plotted against the number of people. Watch the shape. It's not a straight line. It rockets upward, and then flattens as it presses against 100%. At 23 people, we cross 50%. At 50 people, the probability is 97%. At 57, it's 99. And by 70 people, it's 99.9%. A shared birthday is practically guaranteed, in a group that wouldn't even fill a small classroom. The reason the curve climbs so violently is those pairs. Add 1 person to a room of 50, and you don't add 1 new chance. You add 50 new pairs at once. The number of comparisons grows with the square of the people. Quadratic growth, hiding inside a simple party trick. So why does our intuition fail so badly? Because we instinctively count the wrong thing. Your brain looks at 23 people and counts 23, or it counts you against the other 22. Either way, it's thinking in straight lines. But the birthday problem doesn't live in the people. It lives in the connections between them. And connections multiply. It's the same blind spot that makes exponential growth feel impossible. We see the objects, but we're blind to the interactions. And in a connected world, it's almost always the interactions that matter. This isn't a parlor game. The exact same math underpins modern cryptography, where it's called the birthday attack. Every digital fingerprint, every hash, maps data to one number out of an astronomically large set. You'd think you'd need to try about half of them to get two inputs that collide. You don't. Because of pairs, collisions appear after only about the square root of the total. The shortcut from the birthday problem becomes a weapon. That's why secure hashes are so long. If a hash has, say, 256 bits, the birthday attack means its real collision resistance is only about 128 bits. Half. Designers must double the length just to stay ahead of this coincidence. A puzzle about a birthday party quietly sets the size of the keys protecting the internet, and it shows up everywhere you look. In any football match, 22 players plus the referee make 23. So most games on Earth secretly contain a shared birthday. In data systems, in biology, in physics, wherever many things can interact, collisions arrive far sooner than anyone expects. So here's what I want you to carry with you. When you want to understand a group, don't just count the members. Count the connections between them. The members grow one by one. The connections explode. That gap, between how many things there are and how many ways they can interact, is where almost all the surprising behavior of the world hides. 23 people. 253 invisible connections. The room was never as empty as it looked.